Hello everyone and welcome to today's lecture. Today we're going to be talking about a topic known as improper integrals, which is going to be a topic that extends one of the basic ideas from Calculus 2 to a more general footing covers some very, very interesting and useful applications of these types of integrals. That we call improper. So what I'm going to do is review a little bit from Calculus 2 and then kind of move on and describe the first type of improper integral. So in Calculus 2, recall the concept of the definite integral from Calculus 2. This is also kind of better thought of very often as the accumulation of a function on some interval from A to B. In Calculus 2 class, this is denoted with what's called the integral symbol. Then we have an A right here and a B right here. And this stands for the definite integral of the function f of x, which we sometimes term this function is called the integrand over the interval from A to B. So this notation stands for the definite integral of the function f of x from A to B. Alternatively, we can say that this is the accumulation of the function f of x from A to B. Because very often the function f is some sort of density function, either a charge density or a mass density, and the definite integral of that function gives us the total accumulation of that quantity. That's one of the big applications of the definite integral, is to density functions, and this is one of the big physical applications in how we use it. So the idea is that this value is in fact equal to the area under the curve f of x, as long as the function f of x is a positive function. But if the function f of x is positive and negative at certain regions and points in the domain, then we cannot say that it's the total volume. It is always equal to the net volume. This is another synonym that you may have heard in one of your prior calculus courses. So the net area under the curve f of x from A to B. And this is really just the total amount of area where f is above the x-axis minus the total amount of area where the function f is below the x-axis. But so these are all synonymous with one another, and one of the big theorems and ways of computing these definite integrals from your Calc 2 class, you should have seen the fundamental theorem of calculus. And there's actually two parts to this theorem, but the main part that's of interest to us is that the definite integral from A to B of a function f of x, as long as that function is continuous, will be the difference of the antiderivative of the function lowercase f of x at the boundary points. So this is capital F of B minus capital F of A, where capital F of x is the antiderivative of the function lowercase f of x on the interval from a to b. In your Calculus 2 class, you probably saw many different methods of computing this definite integral, such as substitution, integration by parts, partial fraction decomposition, trigonometric substitution, and these are all very, very important to know and understand when calculating indefinite integrals as well, or I should say improper integrals as well. So you're going to want to review a lot of the concepts from your Calculus 2 class for that. And you're also going to want to familiarize yourself with many of the applications of the definite integral, because in a lot of the examples that I'll go over, this is going to be very, very important to be familiar with and to understand. So applications include, but are not limited to, solving for the arc length of a curve, or the total length of a curve, solving for the surface area of a given surface of revolution, solving for the volume of a given surface of revolution, solving for the center of mass or moment of inertia of a given solid of revolution. You might have seen examples and applications to probability theory, which is not a physical application, but it's a super important application in terms of understanding probability in statistics. And you also may have seen some other physical applications. There's calculating total energy or total forces on a given body, or many different other physical examples as well. These are just some very, very interesting applications of the double integral that are typically gone over. Not all of them, but many of them are gone over in a typical Calculus 2 class. So it's helpful to draw a picture. Just to remember and remind exactly what this is representing. So I'll draw a relatively general picture here. We'll go from x equals a to x equals b right here. And we'll draw the following functions. Let's say it goes up, then comes down, and comes up again, and then down, and then maybe ends right here. So this is actually a very common type of function in what's called waves and oscillations. It looks kind of like an exponentially decreasing oscillatory signal, right? So say like a signal that your brakes and the shocks might get when you hit the brakes in your car. But the idea is that it's just kind of going up and then down, up and then down, up and then down. But the amplitude of the oscillation is getting smaller and smaller and smaller. This is a very common signal and a useful signal in applications. So the definite integral of this function from a to b is the net area under this curve. And what I mean by that is that if you were to say calculate all of this area right here, all of the area of the function above the x-axis, and subtract from that all of the area of the function below the x-axis, so this area right here, the value that you get from the definite integral of this function is exactly all of the red area, that value minus all of the blue area, right? So this becomes very clear then what I was talking about before, that if we were to say take the definite integral of a function from c to d, and the function is always positive, so the blue areas from c to d is 0. There's no regions where the function dips below the x-axis. Then the integral from c to d of this function is in fact the area from C to D. But in general, this is not always the case, which is why you can't always call the integral of a function the area under the curve. In general, we can just call it the accumulation of the function over the interval. So the idea is that we want to get at defining exactly what an improper integral is. So if we take this image, and I copied the image down on the next page, I'm going to show you exactly what it means to talk about an improper integral. So the definite integral is sometimes called a proper integral, and an improper integral is an integral where one of two things is true, which is why we separate improper integrals into two separate types. So an improper integral of type 1, I'll make two separate plots here to show an example of each of these two types. An improper integral of type 1 is an improper integral where one or both of the boundaries of the integral extend to infinity, and we want to figure out the total accumulation over that infinitely sized interval. So I'll draw a picture here first to kind of illustrate. An improper integral of type 1 and there are actually three separate subtypes of improper integrals of type 1, which we'll get into a little bit later. But I'll just draw one of the subtypes here, is where one of these boundaries, right, extends, one of the bounds of integration extends all the way to positive infinity. So you don't have a fixed real number right here, but let's say this oscillation function continues forever. Just keeps moving on infinitely long, all the way out to positive infinity. Believe it or not, there still is a sense in which we can kind of think of an accumulation of such a signal, because the signal does go above the x-axis at many different points. It also goes below the y-axis at many given points on this infinite interval. You could say you might want to consider the total limit of the oscillations as the time goes to infinity, if the x-axis is representing time, for instance. But this is one of the types of improper integral of type 1. And we're going to try and make sense of these in this lecture today. But I'll also mention, what an improper integral of type 2 is as well. Just so that you have both of the different distinctions clear from the beginning, from the get-go. And I'll actually draw the third type of improper integral of type 2. This is where the function has a discontinuity at a given point and extends along that discontinuity either to infinity or negative infinity on each corresponding side of the discontinuity. Let's just say at this point right here, the function is discontinuous, and we'll say from the right it goes up to positive infinity. And then let's say from the left it goes down to negative infinity. So it's not defined. The function is not defined at that point. The discontinuity at the point, because the function limit is divergent from both sides. This is actually the third type of the type 2 improper integral in the labeling scheme of the book. You see the discontinuity on both sides. Now it turns out that both of these integrals, both type 1 and type 2, are improper integrals. One, because the first one is because we're integrating over an infinitely sized domain. And type 2, same thing. We're integrating over an infinitely sized domain because the function's blowing up from either side. It's going to positive infinity from the right and negative infinity from the left. And so the size of this integration domain is also infinite. But just because the size of the integration domain is infinite, it doesn't mean that the integral does not exist. There are many, many useful, important examples for which this integral actually will exist and give a realistic answer. Not just realistic, but the exact answer to what it means for the definite integral over that region. So this is, I think, a very good kind of explanation of the difference between the two types. And what we'll do is kind of move into improper integrals of type 1 in this lecture. So to move into this, we'll start by distinguishing what each one of these subtypes of type 1 improper integrals are. I started with the first subtype in my drawing above, and this is the subtype where the upper bound b extends to positive infinity. So we're getting the accumulation of the function over the interval from a to positive infinity. And like you might have expected, this is has a very nice notation here. We just put an infinity symbol where the b is. But don't be fooled. Right? We need to be very, very careful here because we know from our investigation into L'Hopital's rule and indeterminate forms that we need to be really careful when we're using the infinity symbol, and it can't just be plugged into a function. We need to use it in the sense of a limit, and this is why we need to use the limit when we're going through and defining the actual computational procedure for the definite integral. So the definite integral type 1, subtype 1, over an infinite interval where the upper bound extends to infinity is defined as the limit as b goes to positive infinity of the definite integral from a to b of the function f of x dx. So what this is saying is that we have to take first the integral, the definite integral of the function f of x, and then take the limit of this result as b goes to positive infinity. So you can see very clearly that our limiting procedure from L'Hopital's rule, the reason that we started with that is because we're going to have to take limits when doing improper integrals. And if we have the derivative here, this is just going to be the same thing as the limit as b goes to infinity of f of b minus f of a. So in general, the limiting behavior of the antiderivative function as b goes to positive infinity is going to determine for us the value of this improper integral. So this is improper integrals of subtype 1, type 1, subtype 1. Improper integrals of type 1, subtype 2 are the exact same thing in some sense, but we reverse which bound is going to positive infinity. This is the lower bound now is going to negative infinity. It's going all the way back in this direction, all the way to the left on the x-axis. The notation for this is exactly like you might expect. The integral from negative infinity to b of the function f of x dx. And this is exactly evaluated by taking the limit as a goes to negative infinity of the definite integral from a to b of the function f of x dx. which, like you might expect, is the same thing as the limit as a goes to negative infinity of f of b minus f of a. So subtypes 1 and 2 are relatively straightforward and I think easy to understand. So some of the first examples that we'll do will be of these two subtypes. But I will define subtype 3 right now as well, just because it's really important that you kind of get a holistic view of this process and what we're trying to study here. So before I get into defining improper integrals of type 1, subtype 3, what I want to do is define an extremely important terminology that is going to be used for improper integrals. So for improper integrals of subtypes 1 and 2, we say that the improper integrals are type 1, subtypes 1 and 2 converge or are convergent if the corresponding limits exist and they're said to diverge if the corresponding limits do not exist. And be careful because you might think that do not exist just means that they go up to positive infinity or negative infinity. But if the limits oscillate infinitely much, then this is also an example where it would not exist. So be very, very careful with that as you're going through and doing these problems. And a given improper integral will either converge or diverge. So we have only those two possibilities. So with these definitions now, we can really go through and understand what it means for the subtype 3 to converge. So this final picture right here is of a diagram kind of illustrating what it means to have an improper integral of subtype 3. This would be when we're trying to find the accumulation over an infinitely large domain in both directions, so in the negative x direction and in the positive x direction. Like you might expect, the notation for this is just negative infinity in the lower bound and a negative infinity in the upper bound. But we need to be very careful with how we define this. We say that this improper integral exists or is convergent if the following two improper integrals exist and are convergent. But for any value of c in the domain x, the integral from negative infinity to c exists. We add that value to the integral from c to positive infinity of f of x dx. So what we're saying is no matter what value of x you choose in the domain, we'll say c is this value right here, the improper integral from negative infinity to c exists, and the improper integral from c to positive infinity exists. This has to work for all c. Say that this is the definition of what it means for the improper integral to be convergent of subtype 3. This is the exact correct way of defining this, and it's the only real way of doing it nicely. And I want to make a note here. I'll make a note in red with lines. This definition is not the same thing in general as taking the limit as, say, some L goes to infinity of the integral from negative L to L of f of x dx. This actually does have a name. It's sometimes called the principal value of the function. And for certain nice functions, the principal value does coincide with the value of the definite integral, or the improper integral from negative infinity to positive infinity. But for many functions, the principal value, and I'd say many, many more functions, the principal value is not the same thing as the improper integral from negative infinity to positive infinity. And for certain functions, the proper improper, or the improper integral of the function will not exist, but the principal value of the function may exist. So it's very, very important to realize this and to not try to simplify this process too much. A big mistake that students will have is they think the improper integral is the principal value, and they'll go through and calculate the principal value of the function when really they're trying to calculating the wrong value. They need to go through and do two improper integrals in general to compute the improper integral of type 3, or type 1 subtype 3. So what I want to do is go over a number of different examples for you to kind of show exactly what we're talking about. So what I'll do is here in this first example kind of start with a relatively physical, understandable example, especially if you've taken a Calculus 1 course or a physics course, and this is going to be to do with kinematics, or the study of motion. So the idea here is the following. Let's assume that we have the velocity function for a given type of motion. So we'll call this v of t, and just for argument's purposes, we'll say that this is the y velocity. So it's the rate of change of y, the y coordinate of some particle with respect to t, or time. And what we know is that the actual displacement as a function of time, or y of t, from the fundamental theorem of calculus is going to be, well, y at the initial time, t naught, plus the definite integral from 0 to some final time, or not 0, sorry, t naught, whatever our initial time is, to the final time of the velocity function as a function of time. It's the definite integral with respect to t. So this is just some basic kinematics that you hopefully have seen either in a basic physics course or in a Calculus 1 course, or not Calculus 1, Calculus 2 course. But the idea here is that what we're now kind of interested in is using this example now to discuss and figure out what the long-term behavior is of this object. And this should also be y of capital T. So the position y of capital T is equal to the initial position y of t naught plus the definite integral from t naught to capital T of the velocity function. This is just because the velocity function is the derivative of the displacement function y. So what we're interested in this problem is kind of relating this to improper integrals, the long-term behavior of displacement y of t. We want to figure out what's happening with the height, or the displacement y of t, in the long run. Mathematically, what this is just the limit as capital T, the end time, extends all the way to infinity in the long run of y of t. Which is the same thing as the limit as t goes to infinity of y of t naught plus the definite integral from t naught to t of v of t dt. Which is the same thing as y of t naught, which is fixed, plus the improper integral from t naught to infinity of v of t dt. So what we're seeing is that we can directly figure out the long-term behavior in kinematics by taking this infinite limit and correctly figuring out what the improper integral is for a given velocity function. So just for argument's sake, let's say that our initial altitude, our initial time t naught, is at, we'll say, 1 second. And our initial altitude, y naught, or y of t naught, is 5 meters. And lastly, we'll kind of compare two different velocity functions. So the first velocity function we'll look at is if the velocity is, or v of t, is 1 over t squared. So the velocity is decreasing at a certain rate. It's getting smaller and smaller and smaller, all the way to 0 as we get to a larger and larger and larger time. But what we'll do is we'll look directly at what the limit is as our end time goes to positive infinity of this y of t. So we showed that this is y of t naught plus the improper integral from t naught to t, or t naught to infinity of v of t dt. Y of t naught is, we're assuming it's 5, so this is just 5 meters, plus this is now the limit as b goes to infinity of the integral from t naught to b of 1 over t squared dt. And you'll do well to remember that 1 over t squared is the same thing as t to the negative 2 in the indefinite integral of t to the negative 2, or the antiderivative of t to the negative 2 is kind of a reverse power rule. So it's 1 over negative 2 plus 1 times t to the negative 2 plus 1 plus some constant of integration, or negative t to the negative 1. So this is the indefinite integral. You'll remember that from a Calculus 2 course. But so now we get the long-term behavior is going to be 5 plus the limit as b goes to infinity of negative 1 over t. This has to be evaluated at the endpoints from the fundamental theorem of calculus. Oh, and I also forgot to put in t naught here is 1 second. So I'll just plug that in right here. And this is just, for argument's sake. This could be a lot of different values depending on how we're applying this problem. So our final answer is going to be 5 plus whatever the limit is as b goes to infinity of, this will be negative 1 over b minus negative 1 over 1. So this is going to be 5 plus the limit as b goes to infinity of 1 minus 1 over b, which is exactly equal to 5 plus 1, or 6. So what we've shown here, right, is this left-hand side of this inequality goes all the way down. Or the left-hand side of this equality goes all the way down. We've shown that the long-term behavior of this object is exactly 6 meters. For the velocity function, 1 over t squared with an initial position of 1 second and 5 meters, so initial time of 1 second and position of 5 meters, we travel a total of 6 meters as t goes to infinity. So this is a really good example, and what I want to do is contrast this, right? Compare and contrast to the exact same situation, but with a velocity function of 1 over t. Because for the velocity function of 1 over t squared, the velocity is decreasing to 0 as time goes to infinity. For the velocity function of 1 over t, it's also decreasing to 0 as t goes to infinity. But we're going to get a very different answer for the velocity function of 1 over t. These two example velocity functions give us two very different phenomena. For the first one that we just considered, 1 over t squared, this improper integral is a convergent improper integral because this limit exists, and it converges to, the improper integral converges to 1. The total displacement, though, that we're looking for is 6 because it starts at 5. For this case, we aren't as lucky, and we're going to see something very important here. So this is going to be 5 plus the integral from t naught, and this is the limit as b goes to infinity of the integral from 1 to b of 1 over t dt. So from calculus 2, the antiderivative of 1 over t is the natural log of t, and specifically the natural log of the absolute value of t, from b to 1. So this becomes 5 plus the limit as b goes to infinity of the natural log of b minus the natural log of 1. The natural log of 1 is 0. But recall the natural logarithm function, the limit of this as b goes to infinity is actually positive infinity. So this limit is going to positive infinity as b goes to infinity. And that means that this value is positive infinity, and we have a divergence of our y. So the long-term behavior in this case, or y of t for this velocity function, is that the particle just continues to get larger. The y-coordinate of the particle continues to get larger and larger and larger and larger without bound. And this is a good kind of comparison between a divergent improper integral, because in this case the improper integral diverges and in this case the improper integral converges. And so I just took this opportunity to plot this out in Desmos to kind of show that the difference between these two results right here. For the two different velocity functions, we're getting two very different results. The orange curve here is the first velocity function, or I should say the displacement as a function of time for the first velocity function. And the purple function here is the second case, so when the velocity function is 1 over t. The purple here is the y of t for the velocity function v of t is 1 over t, and the orange is the velocity function for the displacement function y of t for the velocity function v of t is 1 over t squared. And I just did this from 1 to 100. The limit of the purple function we found out is positive infinity. So y goes to positive infinity. But the limit of the orange function we found was constant at 6. This is exactly what we see right here. We can even see it if we play the animation from 0 to 100. So I think this is very neat and a very cool example kind of illustrating this idea. So that was a good physical example. Now let's kind of move to more of a mathematical example in which we use one of our many integration techniques from Calculus 2. It'll be some good practice. So let's suppose we want to get the improper integral from 1 to infinity of the natural log of x over x squared dx. Now, to give us some of an idea of what this is going to look like, I'll jump over to Desmos for a sec just to kind of get a visualization of this. It's not always necessary to do this, but it does kind of help a little bit, especially as we're learning the material. So this is a plot of the function in purple here, ln of x over x squared, and I'm just plotting this on the interval from 1 to b, so I can move this b around and we can get more or less of the function depending on if we want it. And basically what we've done is we've shown how to exactly the improper integral is defined here for such an improper integral. When we're integrating from 1 to positive infinity, we need to get the integral from 1 to b. I'll shade what that is because this function is positive. That's just the area under the curve of this function from 1 to b. And then once we have this value of this integral, actual integral from 1 to b, we then need to take the limit of this as b goes to positive infinity. So if this exists, this limit exists, then we say that the improper integral converges. And if it does not exist, we say that it diverges. So this is what we need to go through and do. So this is going to be equal to the limit as b goes to positive infinity of the integral from 1 to b of the natural log of x over x squared dx. And basically this problem now is the problem of first solving for this actual integral from 1 to b, and then taking the limit of this integral as b goes to positive infinity. So the first step here is to attack this integral and figure out how we're going to go through and solve this integral. And sure enough, this is a pretty standard integration by parts integral. So that's definitely a method that you want to review. It's that, along with U substitution, is probably one of the most important integration methods that you'll ever use. But for a U substitution here, for our integration by parts here, this essentially consists of choosing a U and a dv to apply the integration by parts formula that the integral of U dv will always be equal to U times V minus the integral of V du. This is one integration by parts formula that you might remember from your Calculus 2 class, or you should remember from your Calculus 2 class. So the idea is that this changes a little bit when we have bounds of integration. It doesn't really change, it just gets a little bit more detailed here. So this is how the formula changes, and should be rewritten whenever we have bounds attached to the integration by parts. But the process for integration by parts is still exactly the same. We have to choose a u and we have to choose a dv, figure out what the dv is going to be. So our u here, I think, is most easily seen to be this ln of x function. So u is equal to ln of x. And this is just chosen because from integration by parts, du is going to then be the 1 over x times dx, or the u prime dx. U prime here is 1 over x. And it's mainly chosen this way because this function is relatively easy to differentiate, and also that would make this choice makes dv equal to 1 over x squared dx. So this is our v prime dx. It's 1 over x squared dx. And therefore then v is going to be the antiderivative of 1 over x squared, which is going to be equal to negative 1 over x. And when we apply our integration by parts formula, then this is going to be equal to u times v, so the natural log of x times negative 1 over x from b to 1 minus the antiderivative from 1 to b of negative 1 over x, which is v times du, which is 1 over x dx. And so this is going to be ln of b over b, negative ln of b over b. And then when you plug in 1 here, so minus ln of 1, negative ln of 1 over 1. That's this first term. This is going to be 0. And then negative times negative is positive. The integral from 1 to b of 1 over x squared dx. This is negative ln of b over b, and the antiderivative of 1 over x squared, again, is going to be negative 1 over x. This is from b to 1. And so our final result here is going to be negative ln of b over b plus, and when you plug in b here, you get negative 1 over b minus negative 1 over 1. So this is going to be 1 minus 1 over b. And remember, this is the integral from 1 to b of our original function. So ln of x over x squared. So for any finite value of b, the value of the area under the curve that I talked about before and I showed before is equal to this value right here. But we know that what we want is we want this in the limit, because we're interested in this problem in the improper integral, or the limit of this quantity as b goes to positive infinity. So we've just shown what this value is this limit right here. There's the limit of this quantity right here. One over b as b goes to positive infinity goes to 0 as b goes to positive infinity. The limit of 1 as b goes to positive infinity is just positive 1. It stays constant. And then lastly, I'll rewrite this to find our final limit, because the final one in here is the most complicated. It becomes 1 minus the limit as b goes to positive infinity of natural log of b over b. And this can be found by a direct application of L'Hopital's rule. If you remember that exercise that I did the other day in lecture, you'll remember that, and you'll know honestly that this limit is going to be 0, because the natural log function grows slower than any polynomial function. And you can prove that out in general. But we'll just kind of go through and do L'Hopital's rule here to be exact, and get some more practice with L'Hopital's rule. This will be 1 over b, the derivative of the natural log function, and the derivative of b is just 1 here. So this limit ends up being 1 minus 0, or 1. So the area under this infinitely sized curve is equal to 1. Our infinitely long curve is 1, which is very neat. What you hopefully see in this example is that these problems are a combination of things that we've learned and we're learning. Right? We're basically building on our knowledge of Calculus 2 and Calculus 2 techniques, as well as our knowledge of limits. Right? We're using very heavily our knowledge of limits, and this is why we start with indeterminate forms and then move on to improper integrals, because you need to know how to evaluate limits properly in order to properly figure out what an improper integral is. But that will be all for this lecture. Thank you very much for tuning in. I hope you had a great day and that you learned something.